Hello, everyone, and a warm welcome to the concluding lecture in our series on synthetic and biological macromolecules. Polymers are an integral part of modern life. You already know that they are very large molecules constructed from a few small molecules that repeat many times. Earlier, we discussed one of the major classes of commercially important polymers and their formation through addition polymerization. Another general reaction used to synthesize commercially important polymers is condensation polymerization, also known as step growth polymerization. This type of polymerization typically employs difunctional monomers, with each new bond being formed in a separate step. Polymers produced via condensation polymerization have incredibly diverse applications, ranging from soft drink bottles to life-saving heart valve components. For instance, a St. Jude valve uses the polyester Dacron to attach it to the surrounding heart tissue. Dacron is DuPont's trade name for the fiber made from polyethylene terephthalate, which is a polyester. Approximately 250,000 valve replacement procedures are performed annually worldwide, most using St. Jude valves. The valve is secured to the surrounding tissue via a biocompatible polyester sewing ring. This polymer contains many polar oxygen-containing functional groups, which enable strong interactions with heart muscles and facilitate tissue growth. In this lecture, we will primarily focus on two types of condensation polymers, polyesters and polyamides. Our goal is to recognize the components of a condensation polymer simply by examining its structure. The monomers of condensation polymers must have two functional groups. We can represent such a monomer as shown here, where A and B denote functional groups that may or may not be the same, while R represents the remainder of the molecule. Most commonly, monomers link when group A on one molecule undergoes a dehydration condensation reaction with group B on another. You have encountered reactions like this when we discussed the chemistry of amino acids and the formation of proteins. Many condensation polymers are copolymers, consisting of two or more different repeating units. Two major types of condensation polymers are polyesters and polyamides. Polyesters are typically formed by the reaction of a diacid, or a derivative of a diacid, with a diol, an alcohol possessing two hydroxyl groups. Polyethylene terephthalate, commonly known as Dacron, is the most widely used polyester copolymer today, and you saw an example of its application earlier. Polyamides are formed by the polycondensation of a diamine with a diacid or a derivative of a diacid. The best-known polyamide is nylon 6,6, discovered by Wallace Carruthers and his associates at DuPont in 1934. It is named 6,6 because it is synthesized from adipic acid and 1,6-hexane diamine, both of which contain 6 carbon chains. Nylons are widely used in home furnishings, apparel, carpets, fishing lines, and toothbrush bristles, among other applications. Another well-known polyamide is nylon 6, also called Perlon. It is made from the cyclic amide caprolactam and is primarily used in ropes and ties. When caprolactam is heated with a small amount of water, some of it is hydrolyzed to the corresponding amino acid. Continued heating of this mixture leads to condensation and polymerization, yielding molten nylon 6. Note that we use a single-digit notation here because nylon 6 is a polymer composed of only one monomer, which contains 6 carbon atoms. If we represent the monomer of nylon 6 as A, the corresponding polymer can be depicted as a sequence of repeating A units, since all repeating units in the polymer are identical. Nylon 6,6, on the other hand, is a polymer composed of 2 different monomers. If we symbolize these monomers as A and B, the resulting copolymer can be represented as a sequence of alternating A and B units, as shown below. Polymers such as nylon and polyester can also be formed into fibers that, like hair, are very long relative to their cross-sectional area and are not elastic. These fibers can be woven into fabrics or cords and used to make clothing and other useful objects. For instance, nylon fibers undergo cold drawing, meaning they are stretched at room temperature. As the fibers are drawn, hydrogen bonds form between individual polymer strands. Specifically, the carbonyl group of one amide bond forms a hydrogen bond with the amide hydrogen atom of another strand, as shown in this figure. The tensile strength and stiffness of nylons are primarily due to this hydrogen bonding. Various substances can also be added to polymers to protect them from sunlight or oxidative degradation. For example, trace amounts of manganese and copper salts are added to nylons to prevent light-induced and oxidative damage, while also helping to maintain their whiteness. A short walk in most cities is enough to see that plastics are not easily degraded biologically. As a result, it is becoming increasingly important to design plastics with built-in susceptibility to bacteria or fungi. Natural polymers based on proteins and polysaccharides have this advantage. And so one approach to creating a synthetic biodegradable polymer is to use natural monomers to produce a polymer that closely resembles natural materials. Polyhydroxybutyrate is an example of a biodegradable polymer. It is even found in some microorganisms as massive whitish granules, occupying up to 80% of the cell's dry weight. It appears to serve as a storage compound for excess carbohydrates. A copolymer of 3-hydroxybutyric acid and 3-hydroxyvaleric acid is also found in microorganisms and is performing the same function. This polyester forms the basis of a strong, yet flexible plastic used in containers such as toiletries and is marketed under the name biopol. Since microorganisms naturally use polyhydroxybutyrate and biopol for energy storage, they can also degrade them. Biopol and other biodegradable polymers are manufactured by fermentation. However, they can also be synthesized chemically via the polymerization of a four-membered lactone called beta-butyrolactone. The polymerization is initiated by a water molecule that opens the first lactone ring. The reaction is then catalyzed by aluminum complexes and continues through repeated esterification of the exposed terminal hydroxyl group. Biodegradable polymers have found many applications in modern medicine. For instance, until the 1980s, patients who received stitches for a wound had to return later to have them removed. However, in the 1980s, biodegradable stitches were introduced. Once applied to the tissue, these stitches slowly dissolve without releasing any harmful byproducts. Today, biodegradable stitches are made from lactic acid glycolic acid copolymers that gradually hydrolyze over time. Modern synthetic materials, such as polymers, are increasingly used in medical and biological applications. For our discussion, a biomaterial is any material with a biomedical application. It may serve a therapeutic purpose, such as in the treatment of injuries or diseases, or a diagnostic purpose, such as in disease identification or monitoring physiological parameters like blood glucose levels. Whether its use is therapeutic or diagnostic, a biomaterial comes into contact with biological fluids and must possess properties suited to its application. For instance, a polymer used for disposable contact lenses must be soft and easily wettable, whereas a polymer used for dental fillings must be hard and wear-resistant. The most important factors influencing the choice of a biomaterial are biocompatibility, physical properties, and chemical properties, as illustrated in the right bottom corner of the screen. Specialized polymers have been developed for various biomedical applications. The extent to which the body accepts or rejects a foreign polymer depends on the nature of the functional groups along the polymer chain and their potential interactions with the body's own molecules, such as proteins, polysaccharides, and polynucleotides. Biopolymers in the body have complex structures with polar groups along their chains. Proteins, for example, are long chains of amino acids linked through condensation polymerization. In humans, 20 different amino acids combine in various sequences to form proteins. In contrast, synthetic polymers are generally simpler, consisting of either a single repeating unit or, at most, two different repeating units. This structural difference is one reason why synthetic polymers are recognized by the body as foreign objects. Another factor is that synthetic polymers often lack polar groups along their chains, limiting their ability to interact with the body's aqueous environment. Polymers can be characterized by their physical properties. For instance, elastomers are used as biomaterials in flexible tubing, such as coverings for leads and implanted heart pacemakers. They are also found in catheters, which are tubes inserted into the body to administer drugs or drain fluids. Special thermoplastics, such as polyethylene and polyesters, are employed as membranes in blood dialysis machines and as replacements for blood vessels. Thermoset plastics, though used more sparingly, also serve important functions. Because they are hard, inflexible, and somewhat brittle, they are primarily used in dental devices and orthopedic applications, such as joint replacements. For example, if you have ever visited a dentist, you may have noticed that when filling a cavity, the dentist packs material into the cavity and then shines an ultraviolet lamp on it. The light initiates a photochemical reaction that forms a hard, highly cross-linked thermoset polymer. To sum up, in this lecture, you are introduced to condensation polymerization, which occurs when a small molecule is lost during the reaction between monomers forming the polymer. The two main types of condensation polymers are polyesters and polyamides. You saw that when a polymer is formed from two different monomers, it is called a copolymer. We also briefly discussed biodegradable polymers, which are typically made from the condensation of naturally occurring monomers. At the end, we had a short overview of biomaterials, which are biocompatible materials with biomedical applications. Biomaterials are commonly polymers with special properties tailored to their specific applications. In the concluding module of this course, you will learn about the chemical composition of contact lenses. Thank you for your attention and participation.